Okay, so the first worksheet is the electrochemistry problems. That's where I'm at, if you would join me. So, the first question, when silver metal reacts with bromine at 298 Kelvin, a spontaneous redox reaction takes place. Calculate the following for this reaction. E naught for silver and bromine. So we go down to the table and we find silver and we find bromine. So silver is here. Bromine is above it here. So this one, the higher one, keeps the positive. This one, the lower one, switches signs. It becomes an oxidation. And you wind up with positive 0.27 volts. Questions about that? Okay. Then it says find the equilibrium constant. So E naught, we just calculated, is positive 0.27 volts. The equilibrium constant, if you remember, negative NF E naught equals negative RT natural log of K. So N is 2 because the bromine has 2 electrons. Faraday's constant is like 96,000. 485. E naught is 0.27. R in this case is 8.314 joules per mole Kelvin. Temperature was given 298 Kelvin. And then we're solving for K. So divide this by this, and then you use the exponential function to get rid of that natural log to solve for K. Questions about that? Okay, part B, consider both the information in the question and the values that you've calculated in A above. Without doing any further calculations, comment on the likely value for delta G. First of all, is delta G likely to be positive or negative?
Negative.
Negative, because E naught is positive. That means that it does go. It's not a large E naught though. It's not huge. So depending on what K is, that would tell you if delta G is big or small, negative. The more negative it is, that's going to relate more to a larger K value. Questions? Okay. Number 2, a silver electrode is placed in a saturated solution of silver bromide. The half cell is connected to a standard hydrogen electrode, and the voltage is found to be positive 0.437 volts. Calculate KSP for silver bromide. So you could do one of two things here, but the main thing that you have to focus on is that your cell potential is not what it should be. We must not be at standard conditions. So it should be E cell equals E naught minus 0.05. This log of Q. This equation up here. Yeah. So E cell is given 0.437. Silver is positive 0.80. Hydrogen is 0. So it should have been 0.8 volts. Number of electrons is 2 because hydrogen is 2. And then the log of Q can always be replaced with a K if you're at equilibrium. And then you just solve for K. Mm-hmm.
On the answer sheet, on number 2, it shows the work solution, and instead of having a 2 for the end, it has a 1 for the end.
A 1. That must be an error, because it should be 2, because hydrogen is 2. Yes?
Can you work that problem out? Because I don't understand how they got their answer. I don't understand how it turned out to be a whole number of times 10 to a negative power. I thought it would be 10 to a certain power.
Okay, so I don't have a... Let me get a calculator real quick. We're going to take 0.437 minus 0.8, which will give us negative 0.363 equals negative 0.0592 divided by 2, negative 0.0296 log of KSP, divide, so 0.363 divided by 12.3 equals the log of KSP. So then 10 to the 12.3 equals KSP. That's going to be wrong. Let me look at what I get. Sometimes these answers are off, but then sometimes I'm doing something wrong. Hold on one second. One. So this should be 1 over the silver concentration, I guess, is what they're saying. What?
So I see how we get the 7.38 times 10 to the negative 7, because instead of putting a 2 before n, they put 1. And so if you solve the
Yes.
equation with a 1, then you get the 7.38, but I don't know how they got the 5.45.
Okay, so then what you're not solving for Q here. You're solving for 1 over silver concentration, because they're saying that this is just for the silver part. So then once you know silver concentration, we know that KSP equals the concentration of bromide squared. No, just silver times bromide. So KSP equals x squared. So whatever you get for silver, you're just going to square it. That's more difficult than what will be on your test. There's no Nernst equation on your test. And I still stand by the fact that it should be 2. Questions? Okay. Number 3, consider the following disproportionation reaction at 298 Kelvin. So disproportionation, if you remember from redox, means that the same thing is being oxidized and reduced at the same time. So this is being oxidized and reduced. Fe2 plus is gaining 2 electrons to become Fe. That's my reduction. But then Fe2 plus is also losing an electron to become Fe3 plus. That's my oxidation. And then if I balanced this, it would look like that. You go all the way back to redox. Okay? So then I'm supposed to calculate the standard cell potential for this. So I'm going to go on the table. I'll find this reduction. And I'll find this on the table, but as a reduction. So it'll be flipped. And it will just be Fe3 plus 1 electron. And I'll have to flip the sign. So if I go down here, Fe2 plus 2 electrons going to Fe is negative 0.44 volts. And then Fe3 plus an electron going to Fe2 plus is positive 0.77 volts. But I'm looking at the opposite of that. So it's going to be negative. When I add those up, I get negative 1.21 volts for my cell potential. Part B, what does the value that you have calculated in A suggest about the thermodynamic favorability of the reaction? And explain your answer in terms of delta G. Delta G is negative NF E naught. If E naught is negative, delta G is positive, and it is not thermodynamically favored. Questions about that one? No? Okay, consider the following cell that is operating at 298 Kelvin. So I have aluminum and iron 2 plus. Oh, we're skipping this one. I'm sorry. Number 4 we're going to skip because we're not going to do concentrations on this test. And that's it. Anything else on this worksheet that you're confused about?
You said number 2 wouldn't be.
Number 2 is more difficult. They don't have the Nernst equation on your equation sheet anymore. All right, back. Let's go to the summary. Okay, so this one, when solid iron metal comes into contact with oxygen and water, it forms iron 2 hydroxide. So iron goes to iron 2 plus and 2 electrons. That's my oxidation. And this is my reduction. So those two combined. Part B, calculate E naught for this cell. So iron, that oxidation is negative 0.44 volts is a reduction, so that's positive 0.44 volts. Hold on 1 second. So 0.84 volts. Did I read the table right? Yeah. When left exposed to air, the iron 2 hydroxide that is formed in the above reaction oxidizes further to iron 3 oxide. Write the half equation that summarizes the change in the iron. Iron 2 plus oxidizes again. You get another oxidation. Questions on number 1? Okay. Number 2, magnesium metal reacts with hydrogen ions in a vigorous reaction. Write the cell diagram for this and calculate E naught. So, magnesium is going to be oxidized. So it's going to be the left-hand side. So we're going to have magnesium 2 plus, salt bridge, H plus, 2 H pluses, H2. And then calculate E naught for the cell. Well, hydrogen is 0. Magnesium reduction is negative 2.37. So magnesium oxidation is positive 2.37. Write a balanced chemical equation for the redox process. So magnesium is oxidized. Hydrogen is reduced. Specifically, which species is oxidized in the reaction? Magnesium. Its charge goes up. It loses electrons. And would you expect the reaction between calcium and acid to be more or less vigorous? If we go to the table, calcium is below magnesium. So more or less vigorous? More. It's going to have a higher voltage, so it's more thermodynamically favored. All right, number 3. Which of the halogens listed in the table is the best oxidizing agent? Fluorine. Fluorine's at the top. It's most likely to be reduced, so it's the best oxidizing agent. Those are like synonyms in English class. Most reduced, best oxidizing agent. Number 4, we're going to skip. Number 5, what is the role of a salt bridge? It's for the flow of ions to complete the circuit. No electrons go in the salt bridge, only ions. What is the salt bridge usually made from? I think your answers are not specific, but it could be any paper towel soaked in a salt solution, but the best salt solution is a nitrate salt solution. A high resistance voltmeter is not going to take current out, so you'll get a voltage reading. And then when the cell is functioning, the reading on the voltmeter is 1.52 volts. Calculate E naught for the manganese by subtracting copper. That's all you have to do. 6A and B, you can just read your answers on your worksheet that are on the answers that I gave you. All right, that's it. Do you have any other questions for me? Your test tomorrow. Oh, yep.
For 6B, how do we know how do we know the answer?
Hold on, let me read what you're reading so I make sure I answer the question fully. So you would find E naught between chromium and going to iodine, and you would just find that it was positive. That's all. You would just calculate E naught.
Chromium, not the oxygen.
Right, yep, the chromium.
Okay.
Okay, so tomorrow I've made your test. It is 10 multiple choice. I tried to choose the 10 most straightforward multiple choice from the AP test bank. I'm not trying to trick you. I know that we've flown through this unit. I know it's a hard unit. So I chose the ones that are most straightforward. Calculating E naught. Determining if it's thermodynamically favored. Things like that. Don't forget about entropy. And then your short answer, your FRQ, is 10 parts, 10 points. Again, calculating E naught. There could be some older, like, ionization energy stuff on there because we talked about that in this unit. Understanding equilibrium and Le Chatelier's principle and how that affects these cells. If you add more on one side, what's going to happen to the cell? Is the voltage going to increase or decrease? Things like that. That's it. We're officially almost done with AP material. And then it's review.